Hello. Hi. Good afternoon, everyone. Hope you can hear me and see the screen as well. Once again.
Yes,
Yeah. Hi.
yes.
Okay. Okay. Fine. So, yeah, let's start with the final session for today. I think there is a slight flickering in the screen. I think is it so, or you're able to view it clearly?
Yes, yes. Now we can able to clear.
Okay. Okay. Fine. Fine. So, let's start with building the model. Okay. So for building the model, what are all the things you need, and again, so how to evaluate your model, how to calculate the error metrics, and how to compare different models. Okay, so we will see all those stuffs one by one. So before that, give me a minute. I'll just okay, fine. So first thing, we have imported the data. Okay, so we have cleaned the data and we have transformed the data. So all those things we have seen in the previous two notebooks. Okay, so we have done visualization, we have done transformation, standardization, so a whole lot of things. And also we have done a little bit of exploratory data analysis. Okay, so to find the correlation and to find which value has more impact on the output, either it is positive or negative. Okay, now let's get on to building the models. So now, in order to build a model, what you would be needing is you would be needing another new library called scikit-learn. Okay, so all these five libraries are the most used while building machine learning application. Okay, so SciPy is for math, NumPy is for math multiplication, and Matplotlib for plotting, Pandas for data manipulation, and scikit-learn as all those algorithms packed. Okay, so we can directly use it and implement the solutions, right? Okay, so the first thing we will import the NumPy and Pandas as always. So we need these stuffs to import the data. Next, what we will do is we will read the data. Okay, the first thing is we will read the data. Okay, so here we will read the data from this particular repository. Okay, this particular URL, it has iris dataset. So iris dataset, most of you would have already know, but anyway I'll just tell you what is iris dataset. Okay, so this is an example problem. Next, we will see all the tools and techniques with this simple data, because it is already pre-processed data. We don't have to do a lot of stuffs with dealing the data. Okay, it's already pre-processed data. So iris dataset. So here we have three types of flowers: versicolor, setosa, and virginica. So basically, the data is provided as we have sepal and petal. We will have be given with sepal length and width, petal width and length. Okay, so sepal length, sepal width, petal length, and petal width. Based on that, we have to classify what flower it is. Okay, so either it is setosa or versicolor, or the third one, virginica. Okay, so this data is pre-processed data. Likewise, iris, digit data, MNIST data. So all these data are kind of pre-processed data. You don't have to do the data cleaning and all in here. Okay, so we can directly use it for modeling. So we have imported the data as a pandas data frame. Okay, so pd dot read csv. Okay, so pd dot read csv, and if you see the data set how it is, let's do some head. Okay, so this head would return as the data frame. Okay, so sepal length, sepal width, petal length, and petal width, and the corresponding class label. Okay, so here we have to convert these class label into numbers or integers. Either we can do one not encoding, or else we have to do what, integer encoding, like 0 for setosa, and 1 for virginica, and 2 for vesicular, like likewise. Okay, so we will focus more on um, the modeling part. Okay, so we will just quickly skim through these stuffs. Okay, you have shape, you have 150 data. Okay, 150 entries with 5 columns, and if you just do the basic statistic description, okay, you give the describe, you will get all the information like how many numbers of data, 150, everything is equal, and you will get the mean, standard deviation, minimum maximum value of everything. Okay, so it's kind of yeah, so four data, four columns, we have four features are used to find the whether what category of flower it belongs to. Okay, and if you want to see the class distribution, as I said, since it is a pre-processed data, you don't have much of a class imbalance. We have equal amount of data in all the three classes. Okay, but sometime when you are dealing with real data set, what would happen is class imbalance would happen. Like in some data you will have 100, in some data you will have 30, in some data you will have 10. That is too much, but again, a slight class imbalance is acceptable. During that time, what you can do is you can take an average number of it, and you can take the number of samples from all equal number of samples from all different sets. If the data is too low in case of like image processing or something like that, then you can go for augmentation. So there are different augmentation technique for image data, and also for text data. Okay, so that is a different topic on its own. Okay, so anyway, we have classes, we have these three types of data. Okay, so next, let's do some plotting and let's get some understanding about the data. So again, this box plot, okay, is kind of gives us the same thing as this information. Okay, we have to import pyplot, I think. Once import, it would give the normal distribution, the same information in the diagrammatic, in the picture format. Okay, so now let's go to the modeling part. Okay, so along with modeling, we also can do the histogram. So histogram, we can create bins, and we can see how the data is distributed. Okay, so sepal length, it's uniform, and it's not uniform, it's normal distribution. Okay, and sepal width same, and you can see in petal length there is some tall, and after that you see a certain pattern, and also in petal width. Okay, so petal length and petal width, you can see the shape itself would be a different one, and sepal width would be a different one. Okay, so based on the shape and structure of the that particular wing, you get all these data. Okay, and let's do some scatter plot and see how things are correlated. Okay, so the scatter matrix, again we have to import the scatter matrix. So why they have imported everything one by one? Okay, so scatter matrix will but if you see sepal length and sepal width, how they are correlated, and petal length and petal width, how they are correlated, and for all the different features, you can see what is the correlation. So you can do the scatter plot and you can do the correlation. And also you can also plot the class colors. Okay, you can use seaborn to plot the class colors. Okay, and see what features make up what type of data. Okay, so if you see, you can easily find in which type of plot there is more component of a certain thing. Okay, so if there is sepal length is high, then you can see it is mostly iris setosa. Okay, so and again you can see their correlation, and for sepal width it is common, and for petal length there is huge difference. Okay, so we can identify for setosa, it's the petal length and sepal length is always large. Okay, and for versicolor and virginica, it's almost same. So from the data itself, you can understand. Okay, you see how things are there. But here you can see petal width and petal length are kind of correlated. Okay, mostly. But here sepal width is always same for almost same for all the three different classes. Okay, so here the objective is, as I said, based on these effects.
Navneet sir,
Sorry, there is a connection problem. Okay, 1 second, I'm resharing it.
Okay.
Okay, fine. Yeah, I don't know, something problem with the Zoom server. It's not with the system. Okay, fine. Let's start. Okay, so now you have, it's a classification problem because your output is any one of those three classes, right? So it can be either setosa, or it can be either vesicular, or it can be either the virginica. Okay, or any of those three classes. 1 second, my system is frozen. 1 second. Okay, so now if you want to find or evaluate the stuffs, okay, so let's add some point for you to understand what we are going to do. Okay, you'll add a text block, and the first thing is separate them into validation data and test data. Okay, that will be the first thing. Okay, and the second thing is you can use cross validation, tenfold cross validation, okay, to feed in every data to the model. So we will be needing to we need our model to consider all the data, or like the whole entire data set. Okay, so we need to do cross validation. You can pass into it and build different models. Okay, and do the performance measurement. Okay, and finally select the best model. Okay, so this case what we can do is, first thing is we can get the values out of it. Okay, so this dataset dot dataset dot values would give us all the values, and x and y where you have the variable. Okay, so here why we are giving this number is we are trying to slice up. Okay, the first four values are the uh, actual input. Okay, width and petal width and height, sepal width and height. Okay, and the final y is your output variable. Okay, so its output is like this. So here it is, output is like this, iris or whatever it is, you get it. Okay, so that's why we are splitting up into two categories. So now what we do is, we before that we need to split our data. Okay, so we can split our data into training data and testing data. So it's testing data here, but we can also call it as validation data. But in machine learning, there is only two types of data. One is training data to train the model, and to evaluate, you would use testing data, or to find the output, final output testing data. But sometimes you might also use three subsets of data. Okay, so one is training data used to train your model. Okay, the second is validation data. Validation data is used to training means what, in the sense, every time, okay, you try to tune certain variables in the model so that your model can approximate the function. Okay, so just think of it like an radio FM. Okay, for a radio FM, you need to get the proper reception from the radio station. For that, what you do, you would be tuning. Okay, so in all the radios will have only one knob, but just think of like you have 10 knobs. So all the common proper number in all the 10 knobs would give you a proper reception, or else you will get a noise. So similar way, all these machine learning model will have internal variables. You can tune it using the optimization algorithms. So for updating those weights, validation data is used. Mostly in neural networks, training, the forward propagation is taken care, training data is used. For backward propagation, validation data is used. Think of like validation data like internal exam. Okay, so internal exam you used to correct it. Okay, because you have been trained in your classroom, and validation data is used for your internal exam to evaluate you. But test data is a new third set of data. It's like a final exam. You'll know it's unseen, completely unseen. It's a final board exam like kind, where data is completely unseen, everything is new data. You come up with the evaluation. Okay, fine. So here we are just creating only the training data and testing data. But now what we can do is, let's import all the models from scikit-learn. Okay, so all the models import from the scikit-learn, in the sense you would be loading all the models. Okay, so in scikit-learn, so we have linear models. From linear model, we are importing logistic regression. We also have different types of linear models. Okay, let's do control space. You will get all type of models. Okay, so all these things are comes under the linear models. You have logistic regression, you have linear regression, all sort of stuff, right? So we have a linear model, logistic regression, and from tree model we are getting in decision trees. Okay, and from neighbors model we are getting k nearest neighbors classifier. And for LDA we are importing LDA, but we don't need LDA because LDA is used for dimension reduction and analysis. Next, naive bias, you are using Gaussian naive bias. and next we are importing SVM, support vector machine, a support vector classifier. Okay, so don't worry if you don't know about all these algorithms. If you just read off, that is fine. We are importing, basically we are importing models from the five algorithms from the scikit-learn library. Okay, so once we have created, so remember we have seen spot checking algorithms. Okay, spot checking algorithm in the sense, see, initially when you take the data and do your analysis, you can narrow down your choice of algorithm to few algorithms. Okay, but you cannot, like, by seeing the data itself, you cannot find, okay, this would be the right algorithm. You cannot come to that conclusion. Okay, in that case, what you would be doing is, most of the time, as an initial first level of working, you would be having more models. Okay, and you will be trying out every models. Okay, you will be trying out every models with cross validation for all the data combined, and we will see which one works. So once after finding which one works, then you can further work on trying to improve the accuracy further. Okay, so that's how things goes. So now let's create all these models. Okay, and try to use them and try to train them in one shot. Okay, so if you want to train your model, if you want to just create a model and get it trained, you can directly use like logistic regression. Okay, so LR equal to logistic regression. Okay, and you can do LR dot fit. Okay, so LR dot fit, for fitting you can use the uh, X train and X validation. Okay, X train and X validation, and sorry, X train is not defined. I'm getting this. Okay, one second. Okay, train test split is not defined. Train test split is, we have to import it from scikit-learn. We'll import it here. Okay, still we have a lot of things to import. We will import them one by one. Okay, so we have test train split. We have made up the split of X and Y, and we are loading in all the models. Okay, now we are creating logs, and we are trying to train it. Okay, and why we are getting this error? Okay, we have to convert this to integer. Okay, because all these X validation is string data, right? Okay, so the string data, we have to convert them to an integer format. So only then model will be able to take in. Okay, so this is correct. Oh, sorry, I made a blunder mistake. Y train, X and Y have to pass in. So X is Y is like this. And before passing in Y, again, as I said, we need to convert it. Okay, convert all the values to the desired format. For that, what we can do is, we can either see, I think we can either do this, or else we can directly pass in, because all these things are different type of classes. Okay, then you can do lr dot predict. Okay, so lr dot predict, for predict you can pass in the y data, y train data. Okay, so y train, sorry, x validation data. This validation training is kind of, this terminology is being confused. Mostly I use X train and test, Y train and test. So we can see it has kind of given us few predictions. Okay, so based on the new X validation data, so training data we use it to train, and validation data we use it to validate the model. Okay, we predict the model, and we can compare the results. Okay, so but we will come to that in a bit. But before that, what we can do is, let's create a set of models, and we will try to run all the models and try to get the accuracy for all the models in one shot. Okay, so basically this is called a spot check algorithms. In spot check algorithms, let's say we are having a model array, and we are appending all models. Okay, we are using logistic regression, we are using knn, decision trees, Gaussian naive bayes, and SVC model. Okay, so we are taking in all the models in one array. Okay, so we can train them together. Okay, so and okay, there are a few questions in the chat, we'll answer them. Okay, but once we finish this, we will try to answer them. Okay, now let's add, we need a create a results and names to store all the results. Okay, to store all the results in the model. Okay, so now what let's do is, this is name, this is the model. Okay, so name and model, it's a single tuple, we have appended it to our model. So what we can do is, for name model in models. Okay, so you would get models and models and the names for every iteration. Okay, so here is where what we do is we do the cross validation. So before training our model, we would be importing certain things. Okay, so we will import these stuffs. Okay, uh, here let's import the cross validation score. Okay, and also the stratified k-fold. Okay, the stratified k-fold is a type of k-fold where I think one data is left out. I think so. That is like we have a lot of types of k-fold. Basically, splitting up the data into different halves and training on every data. Okay, so training on every parts of the data again and again. Okay, so that's the main thing. So now what we do is we also need certain evaluation metrics, as we have seen. That's also we will let's try to import them. So let's have classification report, confusion matrix, and accuracy score. So all these three evaluation metrics we can use them. Okay, fine. So now we have initialized our models. Okay, now we have our cross validation methods. Okay, now we have our evaluation metrics. Now let's train every individual model using a for loop. Okay, and also get the best results out of them. Okay, so first is k-fold. This k-fold is a single function. You can do it like this: k-fold is equal to stratified k-fold, and split is 10 split. Okay, basically from out of 150 data set, you are splitting them into 10 half. So then initially 135 data will be training, and the 15 will be for testing. For the next iteration, a new 15 will be in testing, another one, the remaining 135 will be in training. Okay, so we do all these stuffs. Okay, and also what we do is we get the cross validation score. So this cross validation score, cross validation, if you see, this cross validation is a function. Okay, if you give control space and see, what you can do is Google Colab has a boot different options. So if you give this and if you put question mark and enter that particular cell, you will get all the documentation about that thing. Okay, so here what it takes is it takes in a estimator, which is the model. Okay, the model is the estimator. It can take x and y. Okay, and you can also get the CV, cross validation. Okay, so if you pass in the cross validation for all these data, this x and y data, it will get the results for the 10 cross validation, like whatever the number we are given here. Okay, it runs for 10 times and will get the data, and finally you can give the scoring, and based on what you have to give the scoring, you can use uh, accuracy. Okay, so let's use this. Okay, let's use all the variables. Okay, but we will not be needing certain things. We will remove it later. Okay, so paste it here. Sorry. Okay, let's still here. Let's copy and let's go and paste it here. Okay, so estimator is our model. Okay, for every iteration you will get a new model. Yes, and data, you have x train and y train. So this is our data for training the model. Okay, so x train, and you can pass in the y train. Okay, you can pass in the x train and y train to the model. And finally, cross validation. So cross validation here, what cross validation we are using? We are using the k-fold stratified cross validation. You can pass it here, so that for every model, for this 150 data, we are split up. I think it would be 130 data. Okay, 130 or 120 data. It would run 10-fold cross validation. Okay, and the scoring is based on accuracy. Okay, accuracy, you have to get the score, right? Fine. So now we will store all these things in a separate variable so that we can append it. Okay, this is CB results. Now what we do is we would append the result, okay, to the results array list, and we will append the names to the names array. Okay, so we will append all those things. We'll also try to print the accuracy. Okay, we'll also try to print the accuracy here. Okay, so let's do this and we'll try to run this. Let's see what happens. Append. Okay, what is the error here? Names dot append. We need name, right? indentation. One second, I'll go there and click enter. I'll go there and click enter. Okay, now it should work. So what will happen is for all the models it will run, and it would give us the results. So for 5 models, tenfold cross validation, your model will get 10 times. And you can see logistic regression kind of gives us 94% accuracy, KNN 95, CART is 93, and naive Bayes is 95, and support vector mission is 98. Okay. So meanwhile, we have got few questions in the uh, notebook. Let's see them. Okay. So yeah, can you show the output for X and Y? Yeah, that we can do. We'll show that. Okay. X and Y can be used to fit, right? Okay, that's a mistake. I've changed it. Okay. Random state one is, see, we initialize random state so that when every time when you run that, you would get the same numbers. Okay, that's why you set the random number. If it is not, you would get different numbers. Okay. K-fold is K-fold cross validation. See, why in the sense, let's say we have this data, we have a training data of 130. Okay, so now we have 150 data. Out of 150, we have taken 130 as training and the remaining 20 as testing. So think of it like that. So K-fold cross validation, what it does is it's a tenfold cross validation. Okay, so tenfold cross validation in the sense every time this data is split into 10 halves. Okay, so let's say it's 15, 15, 15, 15. Likewise, it is split up in 10 halves. Okay, and for every if it is 10 split, and for every iteration, what it does it would use the first data as testing data and remaining as training data. For the second loop, it would use second as testing data and the remaining as training data. Okay, so that's why we do cross validation, so that every part of the data is shown to the model. And now you can see the accuracy, how you are getting. Okay, so support vector machine kind of gives 98% accuracy, but we will see how we can improve that further. Okay. So can we split as train test cross validation using same function, or we need to do another function? Yeah, this function would be enough. Okay, this k-fold and this should be enough. Like yeah, I have another notebook, but we don't have enough time to copy paste it. But I will just show it, execute through them, and I will just show it to you. One second. So how cross validation works? Okay, that's one of the important metric while doing the processing. Okay, so CV techniques is a new notebook. Okay, so let's take this. So this notebook is what has a lot of cross validation techniques. Let's connect it. Okay, so you can see you have test train split. Okay, test train split, you have 1 2 3 4 5 data and 5 input and 5 output data. Now you do the test train split 0.33 percentage. So 3 data is in training and 2 data is in testing. Okay, and you run it, you get, see why random state is every time you run you get the same value, or else for every time when you run you get a different value. That's, now let's come to cross validation score. Okay, for cross validation, yeah, you can do this. Okay, cross validation score is a different metric which would you have to pass a cross validation data, you have to pass CV6. It would by itself split the data into 6 halves and will be trained and give us the result based on every data. Okay, and you can see different types of cross validation. Let's remove this and come here. Okay, so here you can see k-fold from sklearn model selection, k-fold, and you have this. Okay, and you have done your splitting. Okay, split into 2. For every time you run, you can see initially you are getting this as training and this as testing, and next iteration this as training and this as testing, and finally this as training and this as testing. So for different iteration you would get different split of data to train it. And similarly you have k-fold general one, leave one out, it will leave one data out and would use rest of the data. Let's say you have 10 data, it would leave only one out and use 10 for training data. And also you have other types, but this is how cross validation works. Okay, fine. Let's get back to the code. So yeah, you have cross validation setup, you have CV results. So the CV results can take up the cross validation, and you can also pass in CV equal to 6. So instead of passing 6, we are giving the stratified k-fold. What type of k-fold is? Okay, So now you can see the accuracy and how it is performing. Fine. So now you can see SCMS performing quite good, and we will see how we can. Now we have compare our model. Okay, so we have compared all 5 model and we have seen which one is best. Okay, this one is the best one. And now what we can do is we can further improve the model. Okay, based upon the all the results and just to plot things and see. We can do a box plot. And you can see how they are organized. Like you can see here SVM, it's mostly close to what it is giving. Very good accuracy at what it is giving. And okay, now let's what do is, okay, now we have found that SVM gives a better accuracy. Now let's create a SVM on our own. Okay, now let's create a separate SVM classifier. Okay, so this classifier we have created, like a model is equal to SVC and gamma is auto. We will come to that gamma and kernel trick later. Okay, and model dot fit with training data x train and y train, and model dot predict with x validation. You can find your accuracy. So how you find accuracy? You can compare the predictions, okay, with the actual values. Okay, so now we have evaluate the prediction. You have your predictions, okay, and y validation. So when you compare them, you can see what is the accuracy. It's 96% accuracy here. Okay, and let's say now we wanted to plot the confusion matrix. So confusion matrix, you know, right? So which one is correctly classified and which one is wrongly classified, we get a matrix kind of thing. Okay, so here 11, 12, 12 and 6. Okay, so here one misclassification. Okay, so let's think like this is Setosa, Virginica and vesicular, and again this is Setosa, Virginica and vesicular. So 11 Setosa is classified as Setosa, and 12 Virginica is classified as not 12 only out of 13, 12 Virginica is classified as Virginica, but the third one, the 13th one, is classified as the last category. Okay, class A, B and C, here all A as A, and here if you see this is, if this is true and this is predictor, then it is classified as third one. So here one mistake. Okay, basically your diagonal should have the maximum value, rest of the value should have 0. So that's the initial thing. And now you can get the classification report. So even though you have your confusion matrix, you can get the classification report. So classification report, you can import it from scikit-learn and you can pass in the validation prediction. You can see precision for Setosa is 1, for versicolor is 1, but for Virginica it is 86, because this one thing as misclassified as another, Virginica is classified as versicolor. Okay, and you can see the recall is same for both these two things, and this is 9. So you can see if both are high, then the F1 score is high, but if any one of these is high, then it is low, because you know the formula, right? F1 score is 2 into precision into recall by precision plus recall. Okay, and finally you get your output. So you can see the number of classes. We have 11 Setosa, all 11 here, but 13 vesicular, 12 vesicular here, and 1 as Virginica. Okay, and 6 Virginica as correctly. And you can get all sort of averages and stuff involved here. So let's give a quick recap. So we got a little bit of confused in the bit. Okay, but I anyway will recap it. Yeah, you have X and Y data. You are creating testing test data. You are creating train data and test data using the test train split 20%. Okay, random state 1. Every time you run the code, you get the same split. Import all the models. Okay, create a single model and try to train it and predict it. That would be your prediction. Okay, and also you can append multiple models. So you have to do that for one by one. You can import multiple models into a single list, and you can iterate them and get them trained. Okay, and you can extract, you can store the results and name of those models, and you can get the accuracy. Okay, these things. And now you finally got the which model to use from the spot check algorithms. You knew that you kind of found out that SVM is performing better for your data, because SVM always performs better because it's much more complex model compared to these simple things. And finally We have used cross validation to find the accuracy for all models. We have found SVM. We have created a separate model for SVM, and we have found out to 96% accuracy and all those evaluation metrics. Okay. So now let's try to improve the SVM further. So how you can improve SVM further in the sense, SVM has lot of configuration parameters. Okay. If you see SVC, okay, let's do SVC, sklearn. Okay. So let's go here. Let's see what all the configuration properties available. Okay. So this C is a regularization parameter. Okay, regularization parameter in the sense it kind of adds a penalty for misclassification. Okay, so that it can avoid misclassification and can model much more complex function and make every predictions correctly. That is regularization term. And second, we have kernel. So kernel is where, so how SVM works is, I'll just give you a simple glimpse. So SVM works in hyperdimension. Okay, so why support vector mission is, it tries to project the data into a higher dimension and tries to draw a decision boundary in that space. Okay, so that's why it's mission. So the mission term stands for the projection part. Support vector part stands for the support vector, which differentiates the two categories. Okay. So here we have linear, polynomial, RBF, radial basis kernel, sigmoid kernel, pre-computed kernel, all sorts of stuff. But default is RBF. But we can use any of these combinations, because any of these combinations, like sometimes polynomial would work, sometimes linear would work. Okay, so sometimes sigmoid would work. So you should be using all sort of combinations, and degree. Okay, so in degree also, and what if you are using polynomial, then what degree it has to go. Okay, and gamma is value. So you can either give auto or scale. So and also you have certain parameters. Okay, so in this case what we can do is, we have to try out multiple combination of these values, right? In that case what we can do is, we can go for grid search. Okay, grid search is where hyperparameter tuning comes in. Okay, hyperparameter tuning. Okay, so for that, let's import the grid search from scikit-learn, from model selection, grid search CV. And again, grid search uses cross validation. And let's define the model parameters. Okay, defining the parameters. So you can see, so here regularization term we are using zero point 0.1 initially, 1, 10, 100 and 1000. So 1000 means more penalty, 0.1 means less penalty. Okay, so we have got, can you elaborate on scikit-learn? Again, scikit-learn is a library. It has all the models default. Okay, you don't have to write a model from scratch. You can import the model and you can use right away. So that is what scikit-learn. So it is a single package which has all the models. Okay, all the machine learning models it has. Okay, and so now we have these combinations. So basically here we have 1 2 3 4 5 values. Here we have 1 2 3 4 5 values, and here we have 3 values. So basically 5 into 5, 25, 25 into 3, 75. So basically we have 75 combinations here. Yes, so 75 combinations you can create a SVC. So I'm just telling what we are trying to do is, see, this same SVM, you done the prediction. Okay, and you have done the calculation. Okay, so you have done your accuracy. Okay, let's run it one more time. So this is what you get for a normal gamma auto, and the normal function 96% accuracy. Okay, so let's use a different configuration. Okay, let's use the kernel. Okay, so we will use kernel equal to, let's use poly. Okay, or polynomial kernel. Okay, let's use gamma is auto, let it be auto, or else let's use gamma is 1. And C regularization term is, let's use it 0.1. Okay, so if you give this metric, uh where is poly is not there, RBF, or okay, instead of poly I note poly. Okay, so it's poly. You can see this configuration gives you one accuracy of 100%. Okay, so this different configuration. Okay, so this different configuration, all these are hyperparameters. Remember I told hyperparameter, like the FM analogy, you have an FM, you have a knobs, you can tune it anyway. Similarly for SVM, these are all the knobs. You can tune this thing to any number, you can tune this thing to any number, you can tune this to any number. Okay, so in that case we are just configuring in a different manner so that we can get a better accuracy. Okay, so I got a question: is grid search CV one of the technique of cross validation? Grid search uses cross validation for hyperparameter tuning. Okay, cross validation is very simple. You split up data and you use it to predict and get some accuracy value. Okay, and SVC is support vector classifier. So if it is a classifier, you can go like that way. If it is a regressor, you would be using a different approach, because again for regression also you can use cross validation, but for evaluation you would be using mean square error or radial error like that. Okay, and or CV search used for classifier, like CV grid search CV can be used for any model. Okay, it's not limited to one model, can be used for any model. Okay, so now let's do the grid search CV. Okay, so now we have to import it. I think we have imported it here. Okay, so let's create a grid search. Okay, grid equal to, let's use this grid search CV. Okay, so this grid search CV will take in the SVC support vector classifier. It will take in a model. You can see grid search CV will take in any model, and estimator is the model. Okay, and the parameter grid, the number of parameter combinations. So here we have this. Okay, parameter grid is, okay, this parameter grid, and what we can do is we can give refit. Refit is always true. We don't have to mention it. And verbose is 0. 0 means it will not print anything. Okay, verbose 0 will not print anything. Verbose 0 is false. Okay, I have run this, I think. Okay, run this, run this, run this, then run this. Okay, see, it doesn't give anything. Now let's give verbose 3. Verbose is text. Okay, so if you give verbose 3, for every 3 cycle you would get a printing of the accuracy. Okay, now let's do the grid search dot fit. Grid dot fit. So during fitting we pass in the same data. Okay, so here what happens is this grid search function creates the cross validation for these two data set and feeds it to the SPC classifier, trains it, and tunes it. Okay, and gets the error for all, gets the accuracy for all certain combinations of the values. Okay, and even you can use a for loop, but grid search has a lot more advantages. Okay, basically it's a for loop. Okay, so let's see. It is doing the search of hyperparameter for all possible combinations. Okay, so let's scroll to the top. So initially it has c is equal to 0.1 gamma 1 RBF. Okay, and again second c1 c.1 gamma 1 RBF. So basically grid search, right? So it will be running 10 times, and for the next, and again next cycle, 0.1 0.1 poly, and again next cycle, zero point 0.1 zero point 0.1 sigmoid, and you can see the scores are varying. Okay, different scores you get it, and for these things c is 1, gamma 0.01, and score 0.9. Okay, so for RBF kernel you get the score of 91 percentage. Okay, so grid search is used to quickly run through the every algorithm. Okay, and to not every algorithm, every hyperparameters for a single algorithm. Okay, to find which hyperparameter. When you have more hyperparameters, this is not suitable. Let's say you have same hyperparameters in uh, uh, neural nets and other stuff. That also you can do with AutoML. Okay, and also you will be having some certain weights that you would be training using gradient descent. But here it is purely some stochastic combination of different variables. Okay, and we also have other types of optimizers. Okay, this grid search is just uses all sort of combinations to tune the hyperparameters. But there's one thing what I use for my production use cases, Optuna. Okay, uh, Optuna, uh, Optuna, it's a optimization framework, hyperparameter optimization framework, and it can be used with anything. So since few of them asked for resources for hyperparameter tuning, So Optiana is compatible with PyTorch, Chainer, TensorFlow, Keras, Scikit-learn, XGBoost, and all sort of stuff, right? So basically, you define objective and uh, you get the best parameters for it. Okay, but this is simple random combinations, and you get it. So after getting this, now it has tried for all possible combination. Now what we can do is we can get the best results. Okay, so now we can go and print it. Grid dot best parameters. This would give us the best parameter, which gave us the best result, and also you can get the best estimators like how it is done. Okay, so best parameters is 1000 for C, and gamma 0.001, and for kernel is sigmoid kernel. So for these thing, it has performed very good. Okay, so that is what grid search gives. And also with grid search, you can also do the prediction for that particular model. Grid prediction. Okay, grid prediction, then this would give you the prediction. Then you can find the confusion matrix and evaluation matrix for that grid search prediction. Okay, if you see, there is no misclassification at all. Okay, so remember here, for this setting, this only auto, we have set only gamma auto. We have got 96% because it is very simple data set. 96 or 1, getting 1 or 96 is pretty obvious. But when you have the actual data, this would perform very poorly. Okay, about 80 or 70 or sometimes even 50. In that cases, you have to focus on feature engineering as well, and also selecting the right model and selecting the right hyperparameters. Okay, that's where the key thing is there. So now we have used the, now we are, see, if you compare things, first thing, we have used cross validation to find which model is best suitable for our data. And second, we have used grid search CV to find the optimal hyperparameter for the chosen model. Okay, so those are all the two things. And yeah, and finally there are a few things that while preparing for the while creating all these notebooks, I found that those things online. Okay, so if you like, most of you would not know or not heard of all these algorithms. Okay, all these um, linear regression, logistic regression, or KNN, or CART, classification and regression trees for decision trees, naive Bayes, and support vector machines. But if you see, without even knowing the internal working mechanism, because you don't need to know the internal working mechanism, because you have uh, cross validation like methods to find the right model for your data, and also you have grid search and other optimizers to find the right optimizer for your model as well. Okay, so all you have to do is get the data, transform the data, analyze the data, understand the data, and get the most significant features, and use those features to train the model. So that's all you have to do, right? So you don't need to know how SVM works, you don't need to know the math, you don't need to know gradient descent or anything. Okay, to get started, I'm telling. But anyway, if you are trying to pursue a career in AI/ML, then definitely you have to know that. But again, that's the thing. So you don't need to understand everything, you can directly do machine learning. Okay, and you don't need to know how algorithms work as well, and you don't need to have Python pro programmer. A decent Python programming knowledge would be sufficient. And also you don't need to be machine learning expert in order to do the ML modeling. And finally, these are all the steps. Okay, so data loading, data analysis, modeling, tuning, training, and all those evaluation metrics. Okay, so now what we will do is, this is pretty much same. Okay, same, or else the procedure, the general procedure to build any machine learning model. Okay, but here one of the important step we have missed. So here we have directly imported the data, right? So here we have just imported the data and does the split, right? This is only just literally 5% of the code. Let's say we have 50 lines, this is, let's just 3 to 5 lines, like less than 5 to 10%. But in your actual code, the data transformation and processing part will be 80, accommodating 80% of the code. Okay, so that is what happens most of the time. Okay, fine. So let's get to the actual coding. Let's take some real data. Okay, and we can try to do that. Okay, meanwhile, we've got a question. If all the models already there, what can be a researcher's objective in doing research? Okay, that's a interesting question. That's a question most of people ask me. Okay, see, models are there. Okay, you can do two things. One is the domain, okay, the one is the data, and the second is the algorithm. So either you can take an existing algorithm, okay, and try to fit it to a different domain. Let's say in computer vision there is CNN, okay, and there are still a lot of domain left. Let's take life science, marine engineering, geological space, okay, or else humanity, medical, autism, language. So we have different domain, okay. So what you can do is, if you are a domain expert, you can collect the data in your domain, okay. Data collection itself research, okay. It's not something very trivial job. It's a very tedious job, and lot of papers. If you see the conferences, 50% of the things will be on data collection, feature engineering, and how to convert feature. Let's say my friend is doing biomedical, like brain computer interface at NTU. So she has a CNN model that is defined, but her job is to collect the data from the brain signals, apply filters, transform it, and make it suitable so that she can use the CNN architecture for her brain signal data. So researchers, what they can do is, they can have researchers having domain knowledge, they can collect the data in their domain, and they can see how they can make use of the existing algorithm for their domain. So that is one thing. Second thing is, you can come up with novel architectures, okay, new methods, new technique, because still machine learning is going in a narrow direction. So training with data, there are a lot of different techniques like probabilistic based methods, mathematical based methods, different security issues, how to productionize all these models. So a lot of scopes are there, it's not limited. So basically, if you're doing scikit-learn, then it is that much only. All everything is there. There is no point in doing research. A developer itself can do all sort of stuff. But if you want to get do research, learn the math, try to build the algorithm, more complex, sophisticated algorithm, or else try to apply a algorithm for your domain. Okay, to collect the data, pre-process data, you can publish your data, and again you would get citations and get it published in top conferences. And yeah, you can do that, right? So yeah, that is there. So this is pretty much the same flow for any machine learning model. Data analysis, see how the data is distributed, their correlation, covariance, all sort of stuff, okay. And again, everything comes under EDA. And evaluate, build models. So first thing, we are creating testing data and training data. We are building multiple models. This is called as uh, spot check algorithms, okay. So spot check algorithms, you use cross validation to find the best model for your data. SVM works good for this iris classification. Sometimes naive bayes would work, sometimes logistic regression would go. It's not that SVM would work all the time. Sometimes decision tree would work. It's not up to our knowledge, okay. And again, once you have chosen your model, then you can go for grid search CV to tune the hyperparameters of that particular model, that single model, okay. And you use evaluation, uh, confusion matrix, precision, recall, F1 score, and that's done, okay. So that's what you do. So now let's do some actual mm, uh, actual thing, okay. So let's create a new notebook. So here we are going to import some new data, actual data, and try to do some try to apply the same technique to get some answers out of it, okay. Fine. So what we do is, let's import the upon the uh, disease, okay. Based upon the features what they have given, you have to find whether this person is having an heart disease or not, okay. So basically, the cholesterol level, the size of something, what all there. So based on all those things, you can classify whether the person is having a certain thing, disease or not, okay. The first thing, I'll just give us name. You see here, heart DICAS disease data set, okay. So let's also try to anyway, GPU will not be used, but again, just to occupy GPU for some time, because see, scikit-learn can occupy GPU, but this scikit-learn cannot occupy GPU. Only TensorFlow or PyTorch can make use of GPU. But there are plugins what you can do that is able to make use of the GPU to run the computation faster. Okay, so here it is a very big code. I'll be copy pasting a lot of stuffs, but I will be explaining them. Okay, first and foremost, import the libraries, import the plotting libraries. Okay, from scikit-learn, import linear model and import logistical regression. From ensemble models, you get random forest, AdaBoost, and gradient boost. And we have mentioned k nearest neighbor in our title. Okay, we will see k nearest neighbor is very simple. I have a small animation for you. K nearest neighbor is the simplest of models. That would be the first step, even before linear regression. Okay, so we are importing all these models. Okay, from tree, addition trees, from nearest neighbor, knns, SVM, SVC, and linear SVCs. Okay, naive Bayes, Gaussian naive Bayes, and model selection, test train split. So we have imported all these data. Okay, and the second thing is create the data frame. So we have created it from a CSV data of heart disease. Okay, so heart disease data dot, this is data dot head. You can get some sneak peek. Okay, it has age, gender, CP, and trust, BPS, cholesterol, FBS, all these things, and the target is yes or no. Okay, so whether either they have heart disease or no. So based on all these parameters, we have to find whether the particular person has a heart disease or doesn't have heart disease. Okay, and if you see data shape and size, it is all about 303 rows and 14 columns. Okay, and this is our target column. So based on all these 13 columns, we have to find the target like yes or no. Okay, so next let's do uh, data dot info. So this info would return us the integer column, float column, like everything is integer column. Not a lot of type conversion is required. Everything is an integer column. Okay, and let's do some describe. Okay, data dot describe to get the basic statistical values. So what is the mean? 54. Okay, what is the minimum? 29 and maximum 77. And for target, you can see target is mostly it is 1. I think maximum is 1 and minimum is 0. Okay, so and it's 1 and 0 only. It's not a minimum or maximum like that. Okay, so we can make use of all these things. Okay, and also we can also do the correlation. So here, remember, here we have done a correlation map, right? So before that, here, yeah, so we can take a data frame and we can do the correlation dot COR to find the correlation. We see whether they are anywhere correlated. Okay, so run this and you get the correlation map. Okay, so what affects the target? So you can see these two things. This is positive, this is also positive. So exchange and thalage. So I don't know what does the exact mean. Look, let's see this. Okay, so UCI hard data set. Okay, let me say hard. So if you just search online, it will take you to the archive UCI dataset. Okay, and you can also get it from Kaggle. So here you will have explanation for all those variables. Okay, you can see patient identification number and stuff, and cholesterol. Okay, serum cholesterol level, smoke, either they are smoking or not, yes or no, and for every different values. Okay, so you will have a maximum heart rate achieved, that is THLCH. So you don't have to blindly go with the column names and correlation. You can also check with the description. So before data collection, wherever you are collecting data, please go there and check for the data meaning and definition. You can see CP spine type is typical, atypical, non-typical. We have different categories. So since it is data collected by something, so here you can see here, this is also research. You can see a lot of papers being researched, published on this, and a lot of citations also for the same paper. Okay, fine. And yeah, that's the data. So you can see which feature affects the target most. This one, and also this one, old peak. Okay, what is old peak here? uh, Old peak is ST depression induced by exercise relative to rest. Okay, so we have and slope, upslope, flat, and down sloping. So all these things we have, we kind of affect the it's not fully correlated, it's not one to one, only target is one to one because it's the same variable. Okay, but rest of the you can see, you can leave this, it's 0.8, you can leave this, but leaving these four, it was also 0.1, we will leave all these four things, but rest of the features, everything is either positive correlated or negative correlated up to some extent. Okay, maybe 0.4 or 0.3 should be seamless, but that is fine. Okay, so we can use them to train a model. Okay, now let's do some feature engineering and see the missing values. So missing values, you can do the isnull.sum. Okay, data dot isnull.sum. Oh, sorry, sum has to come outside. Okay, so data dot isnull.sum. Everything is no missed value in any of these values. Everything is full. Okay, fine. And now if you see the data column, data dot columns. Okay, data dot columns, you would get all these columns. Okay, age, gender, and CP, this one, all these stuffs. But this is kind of pretty confusing, so that what we have done is we have kind of having a new set of target variables. Okay, new set of column names. Basically you can use this: age, gender, chest pain, type, resting blood pressure, this is resting T rest blood pressure, serum cholesterol, flat fasting blood sugar, rest ECG, maximum heart rate. Okay, maximum heart rate is this one, and exercise anigna is this one, and state depression, slope, number of major vessels is CA. So it's more meaningful, right? So let's change the column names. This way you can use pandas to change the column names. Okay, so data dot head, you will get the column names, right? So you will get the change in column names. So all these things you have to done before doing the analysis, because you can easily understand what column you are dealing with. Okay, fine. Now let's do the data processing. Okay, data processing and transformation step. So data transformation and processing step, what you can do is, you can we are using in different values. Okay, let's say we have this particular column, uh, thala thalassemia. Okay, something. Okay, so we are trying to replace it with some numbers, because see here we have 2, but it can have zeros and ones. Okay, so basically replacing the less frequent and less frequently occurring values to reduce the noise of the model. Okay, so less frequently occurring model is 0, and we replace it with 2, and for ECG we have 2, we replace it with 0. Okay, so that is very less, like very, it's not that significant. Okay, and also let's try to drop out certain outliers, that is called outlier clipping. All these things comes under data pre-processing. So we do data dot drop. Okay, drop and np dot wherever, okay, there is maximum heart rate is less than 80, or else serum cholesterol is greater than 150, so it would return as the index. You can use the index to uh, drop it. If you just run this, you can see, so it's an invalid syntax. Okay, if you run this, you can see false and true. Okay, basically it returns as false and true, and you can take the first number and you can use the np dot where to find where it is there. Okay, right. And finally let's get the heat map done. Okay, so heat map, seaborne simple heat map. Okay, uh, go there and run it. So this heat map would give us the thing: light color is negative correlation, strong dark is positive correlation, and intermediate is no correlation. So you have certain dark color in these region for target 1, 2, 3. These three are significant positive correlation, and light colors, this and this four, and again these two, they have significant negative correlation. Okay, so you can use all these stuffs to find which model is performing, like which feature is more significant for the output. Okay, now let's split up the new data. Okay, so now we have the correlation map, and let's see how the correlation affects, like we are creating the correlation map for target. Okay, and we are sort values by this particular target. Okay, so how we are seeing how every value is affecting the target value. So you can see chest pain, the same result in number format. Okay, so chest pain is 0.43, maximum heart rate is 41, slope is 34, ECG is 0.18, and this one is 0.002, 0.02. And target is a gender, thalassemia, number of major vessels, depression, and all sort of stuffs, right? So you can use the first three of this and last three of this. Okay, so this is what this gives. And finally, uh, we go for model training. So we don't want to drop any of those values. If you want to drop, we can drop these two things. Okay, which two things is the columns which doesn't have significant impact, the 0.002 columns. Okay, these two columns. Okay, but we don't have to do that because only apart from this fasting blood sugar, rest of the features is more than 0.1 percentage. Okay, so we can use the entire feature space. And the next step would be what? To create the test and train split. Okay, so here we have x is equal to drop target. So if you drop target, this target column will alone will get removed. Okay, and you will have the rest of the columns in the date in the x variable, and you take the data target and set it to the y variable. Okay, then you do the split, x test and y test, and do the split. Okay, so this is your train and test split you have. So now let's build some simple classifier. Okay, let's build a decision tree classifier. Uh, okay, let's build a decision tree classifier. This is a decision tree classifier, and you do the fitting with the x train and y train. Okay, and now you do the prediction. So you can see all these things uses the default properties. So all these things are default parameters, right? So now we will try to get the accuracy. Okay, accuracy for test prediction, uh, accuracy. This is accuracy, and this is for test data. This is for train data, and this is for test data. Okay, uh, test accuracy, train accuracy, and test accuracy. Okay, so we get both these two things. Okay, and let's try to print it, and we'll see how much what is the accuracy we are getting in. Okay, so for training accuracy we are getting this, and testing accuracy we are getting this. Okay, training and testing accuracy, you can see good for test training accuracy it is performing 100 percentage. If it is 100 percentage, then what it is overfitting. Okay, so since I'm we don't have like we are like I'm not supposed to teach decision tree in this session because we don't have time for that. But decision tree is purely rule based model, and what it can do is it can build rules for all the data, all the different rules you have. Like basically decision trees are prone to overfitting. Okay, because the tree keeps on growing. Okay, as long as it is able to make a proper split. Okay, but for training data you are getting very good accuracy, and but for testing data you are getting poor accuracy, just only 70 percentage, then it is a overfitting, right? So yeah, someone had explained data dot drop. See, data dot drop is, I'll try to execute it. Okay, so now you have this data dot drop dot head. So as I said, in pandas data frame, whatever the function you apply upon a data frame would return a new data frame. Okay, so data dot drop dot target axis one means column axis. Here you can see there is no uh, target variable, and also you can give this one as well. So if you want to drop this one as well, you can give it like this. Okay, so we can drop uh, two things, two columns. So how many columns you need to drop, you can column, because basically target is our output, right? So we'll be removing those things. So that is what drop functions. And after dropping, we are putting it to a variable x so that we can use it. And data dot target would give us the output alone. Okay, this would be the data dot target. Okay, this is the data dot target and the output alone. So input and output we are trying to split. So that is where the target and stuff comes in. Okay, yeah. So now we have decision trees, and we have got some decent accuracy. For training data it's always will be more accurate, but for testing data it's not that accurate. But if you are using logistic regression, then you will not expect this result. Okay, so let's copy the logistic regression code from here. Okay, and let's see how logistic regression is performing for this particular data. Where is logistic regression? Yeah, we have this one. Where is it? Okay, here, not here. Okay, logistic regression, and we do the fitting. Okay, and let's use the same prediction, and we'll do this. Okay, test, train, split, and finally print them. Okay, so instead of decision tree, we use logistic regression. So now let's get it trained. You can see again, logistic regression also kind of gives us 100 here and 70 here, but because it's not linear models, not able to model these complex data and all. But fine, we will try to improve the accuracy. So next what we will do is we will try to use a new type of model called a random forest classifier. Okay, so random forest is pretty much same as decision tree, but in decision trees we only create one tree. Okay, that's why it is susceptible to overfitting. But in random forest we would create hundreds of trees and we would average the result. So that is what happens in the random forest. Okay, so you do the random forest and you can find the test accuracy and train accuracy. Okay, accuracy random forest, you print it and you get it. Okay, so a random forest is awarded to used to prevent the overfitting. You can see here for training data it is 100 percentage, and for validation data it's just only 70 percentage. It's overfitting. Okay, but here you can see for training data also it is given close to 90 to 95%. Then it's a good number. Okay, it's not a bad number, it's a good number. Okay, and we also have other types of models. We have boosting and bagging. Okay, we will neglect all those stuffs. Okay, we'll do gradient boosting. Okay, gradient boosting can give a good accuracy. Okay, ACCGB and test GB. Okay, sorry, ACCGB comma test GB. You can see again gradient boosting gives 99 here and 98 here. It's not that good. Let's try SVM. Okay, so SVM we have seen it is performing pretty good, right? So let's do SVM and let's see how what SVM is giving. And so instead of using this, what we can do is we can use the iterative method to find which one is giving the better result. Okay, let's do that here. So yeah, here we have a list of models. Okay, do we have random forest here? No, I think we will add them. Okay, so let's add them. So first thing we have logistic regression. Okay, we have Gaussian naive, we have decision trees, and let's add up the random forest classifier here. Okay, let's add up random forest here. Okay, let's add up random forest here. Models dot append. Okay, and SVM. Okay, and it's not SVM. It's a random forest. Okay, and we can pass in the model what we have created here. Okay, random forest and gradient boosting. We can pass in GB. Okay, models dot add, and you can add up the GB here. Okay, so we'll try to add up all the models here. Once again, it got stuck. Just taking some time to scroll. Okay, so let's add models dot append, and it is gradient boosting, and we are passing the model. Okay, I think it zoomed out a little bit. So now we have all these models in one shot. Okay, now we can do the training. Fine. So score is calculated or decision tree instead of putting the same accuracy. Sir, kindly share the notebook on the chat box. We'll do the same thing simultaneously. Okay, fine. I'll share all those notebook in the chat box. As per your request, you can now use it. Okay, one second. Okay, I'm just changing it. Okay, anyone can use it. So please make a copy of it, but don't miss out the session. You can play with these notebooks later as well. I will share all the slide and code to the organizing team, Mission Vidyalaya, so that they will email it to you. Okay, so basically we have all our models set up. Okay, now let's do the cross validation. Okay, let's do this thing and we will see which one is performing better. So in order to do this, we need to import certain things. Definitely would not work as expected. We need all these stuffs. Okay, and let's add it here. Okay, let's try to run it. And also results not defined. Again, we need these things to capture the results. Okay, put results here, run it, and again run it. And you can see all these things are training accuracy. Okay, training accuracy, and it's purely based upon the X train and Y train. And you can see random forest kind of gives 80%, but we can tune it much more better to get the result. But you can see initially we have just run random forest separately. It have got us very good result. Okay, but uh, when you pass in the when you pass in the X train using the cross validation, you can see the accuracy kind of drops. Okay, so that is how it behaves, and we can also find the cross validate other scores for all these models using these techniques. Okay, but this is the basic thing. Now let's try to take any one of things. So here we have seen, okay, random forest is showing some good progress. Okay, so we can use random forest and we can do the hyperparameter tuning on random forest, so that we will have a very good tunable data for the random forest. Okay, so yeah, so let's go with random forest. One second, I'll just import the random forest and we will try to do the hyperparameter tuning for random forest. Okay, so I will see which one gives better accuracy. So here mm, let's do this. Okay, let's implement the same thing. I have a notebook. Let's implement what are all the things in the notebook right away. Okay, so first is decision trees. Decision trees would give us this result. Second thing is random forest. Random forest would give us this result. And third is ADA boost. Okay, ADA boost would give us this. Okay, and fourth is gradient boost. Gradient boost is this. And finally, and next we have logistic regression. Logistic regression is this. Okay, and now you do k nearest neighbor. Okay, see, if you see, everything is kind of same method. You just initialize the model, do the fit, do the predict. So scikit-learn is that simple. You can write your implement your logic in one few lines, like 3 lines of code. So now we have svc, and also we get the score for svc. Okay, now finally what we do is we have a separate function. I have used this code to solve a problem. Okay, if you run this, you can see model result. So all the model, random forest, decision tree, gradient boost, ADA boost, logistic regression, support vector machine, naive and knn would give us different training result, would give us different testing result. You can see knn performs very poor because it is not able to map the function. At the same time, it is not able to get a good accuracy in the testing score as well. But if you see naive bias, it's kind of vice versa. You can see there is less training accuracy, but more testing accuracy. Okay, but random forest is doing a good job. Okay, so let's tune the random forest for better accuracy. Okay, again, let's come to grid search. So grid search is a very big code. I'll explain it. Okay, so uh, random forest has uh, branches. See, basically in random forest, you are trying to build a tree. While building tree, you will be choosing uh, which features to make the decision. Okay, for that you would be using Gini gain or Gini impurity or entropy. Okay, entropy would be using. Okay, and also minimum sample leaves. Okay, how many leaf a tree has to be having, and minimum sample split, and n estimators, how many tree have to build, either 100 trees or 400 trees or 700 trees or 1000 trees or whatever it is. Okay, so let's run this. But I have run this particular code already. If you run this code, it would take approximately 29 minutes to finish this process. Okay, so 29 minutes in the sense, it will take more time. Okay, I'll show the example code. So what I'm using as a reference. Okay, so let's show the example code. This one. Okay, so if it is this code, so this code is already run. Okay, and if you see, sorry, once again, let's zoom out a little bit. Okay, so here it is. All these different criteria. Okay, and we are using grid search also, grid search CV and randomized search. And for random forest classifier, the initial configuration we are giving n estimator as 100 and a max features auto and all sort of stuffs. And grid search CV, we don't need this. Grid search CV, it uses it takes in the model, takes in the parameter, okay, different combination, and jobs is -1. We pass in all these things. Now you do CL of flit, and you can see for 1 2 2 into 1 2 3 4 5 6 6 into 1 2 3 4 5 6 7 8 8 into 1 2 3 4 5. So literally 6 into 8 into 5 into 2, I think more than 200 combinations. For all the 200 combination, it would do a threefold cross validation and it would give us the result. Okay, so if you run this, you can see total 1440 fits, and it takes 29 to 30 minutes to finish the entire process. Okay, and if you see the better performance, 65th one is the better performance because it has the parameters like criterion genie, minimum sample, and all sort of stuff. Okay, so now let's use these best parameter to build a model. Now we are creating rf.best. So by running this grid search, out of 1440 combination, we have found one best fit which gives us maximum accuracy. Okay, so you can see split 0 score, split 1 score, split 2 score, and all the mean score. Okay, so this split is for cross validation split. Okay, fine. So now you can see the best score, random classifier best score. You train it and you get the best score like 0.9, and for also you get 1 most of the time. Okay, and ROC and AOC also, it's pretty much greater than thing. Okay, so ROC, as I said, it's used to find the threshold for what value it has to be or what threshold to choose. And AOC, area under curve, used to compare multiple models and see which model maximum covers the data. Okay, so that's where ROC and AOC comes in. And the same thing we can do for logistic regression as well, because even logistic regression had shown good accuracy during the random process. You can see logistic regression is 86 and 81. Okay, so here you are using logistic regression, and still it has penalty term, lasso and rigid regression, L1 and L2, regularization term, solver, what solver it is, and dual. Okay, and again you do, it takes 3.8 minutes, and you get the best model, and the best score is 88, 86 and 88. So classification score, you can find this for decision tree is pretty much better than this. Okay, better than the thing. Okay, so this is the best hyperparameter. Okay, so that is how you build a model. So for this hard classification problem, this model is the better model. Which model is the tree model? Okay, so the tree model, what we have created, the best parameters, this model. Okay, lost regression, where we have built a model once again. Okay, rf.best. So you can use this rf.best. I'll try to reconnect. You can use this rf.best to do the predict. Okay, DICT, use do the predict, and you can classify, and you can feed in new data. Let's feed in the uh, uh, X test data itself. Okay, let's feed in X test data and see what all the results we're getting. I hope the session is saved. Okay, so yeah, the session is saved. So we can use this to get the result, and also you can calculate the accuracy. Okay, so let's take the classification report. Okay, and let's use in like we have this, and let's use rf.best. Okay, rf.best, and let's print for rf.predict and this. Okay, so it's supposed to give maximum accuracy. I'm getting low accuracy. Rf.less, and the 67 is the maximum. Okay, so basically the idea is the best model is the uh, best hyperparameters for the tree, random forest tree. So that is what you get. So if you classify based on that, you would get the maximum result. Okay, so this is for random forest, and our best, and this is for LR best. Okay, for logistic regression best. So, and if you print LR best, you can get the configuration for LR best. C is 24, and weight is thing, and maximum iteration 1000, and multi-class penalty L2. But if you simply create a linear logistic regression, LR is equal to logistic regression, you can see the default parameters is what? C is 1.0, class weight is none, and you can see intercept scaling is nothing, and maximum iteration is just 100, but here it is more. Okay, and penalty is L2, and here we have used same penalty. Okay, so basically tuning these values, all these things are hyperparameters that a model can take in. So tuning all these values, that is what a grid search does. So you can pass in different combinations of these parameters as a tunable parameter property, parameters for logistic regression model. Where it is? Okay, yeah, here it is. You can pass in these things, and out of this, grid search would give you the best one. Okay, fine. And again, cross validation used for comparing models. Grid search is used for getting the best hyperparameters, right? So that's all about the machine learning modeling. Okay, finally what you do, you save this model as a pickle format. Okay, let's take you have logistic regression. This logistic regression will have a coefficient, I think coefficients or intercept. This will have certain weights. Okay, this logistic regression have certain weights and stuff. Then you can store it as a pickle file. Okay, pickle is a format where it can store the entire Python object. Okay, pickle example. Okay, let's see this. So you take this pickle file and you store the model. Okay, you save the model, and you can reload it back in any of the environment, even if it is mobile or server. You can reload it back, and you can do the prediction. Okay, so we are getting a lot of questions. Okay, we'll take some of them. I think we are almost at the end of the session. Excellent session. Thank you so much. And feedback link, yeah, they will be sharing to you. All the notebooks I will correct it, so that a lot of clumsy things are there. I will correct it and will add some comments for you to read it out and understand the code, and I will share it to the organizing team, so that they can share it to you people. Okay, and what else? If all the models same thing. Okay, data dot drop same thing. Score is calculated or decision tree instead of LR and same accuracy. Fine. I think I would have made some mistake. I was running quickly. uh, and thank you so much. And with that, one final thing, I'll just quickly jump onto the slide. I think it's reloading, so this internet and my system is kind of irritating me since morning. Okay, so we'll go back to the slide. We have final 2 minutes. Okay, we have 2 minutes to end. And what else is left? So that's pretty much what we have done for today. Okay, so build model, evaluate model, choose the right model, cross validation, evaluation metrics, choose the hyperparameter using grid search, and model deployment. Okay, so that's all about the thing. And finally, feel free to reach out to me. I'm currently working at Nunere Labs, being involved in education, research, and also software development. And also, I'm involved with a lot of communities, TensorFlow user group sponsored by Google and Cometry AI community. We have been teaching and educating people on AI and other latest technologies. Especially my expertise is on AI and IoT. Okay, so feel free to reach out to me. Already few of them pinged through LinkedIn. If you just Google Navneet Malingan, you can get my links. I'm on YouTube and stuff and all. So over the time, I have created some decent amount of content on internet. You can easily find me. Feel free to reach out to me if you have any doubts, queries, collaboration, or whatever you have. And again, thank you so much for the mission Vidalya, for having me as a part of the Ramakrishna team. And thank you, Sridhar sir, once again for believing in me. So always he gives me the opportunity, and I tries to not disappoint him, and by giving the maximum what I can. So thank you so much. See you in another day.
Uh, Thank you, Navneet, for your efforts and your
Okay,
making
sir.
sessions live. And
Thank
more
you,
to
sir.
say, there is a more feedback and best feedback had come from the participants. Their
Okay, sir.
encouragement is our encouragement.
Yes,
That
sir.
because their feedback and their way of thinking is being changed because of your
Okay.
presentation and other things over there. So
Mm-hmm.
our sincere thanks to you first, and also
Thank you,
to the
sir.
participants who have taken all the efforts to be with us. Nearly about 80 to 85 participants are there in lively, right from morning to evening. That
Yes,
itself
yes.
is encouraging us that these people are quite interested and they will be able to take something from us and put into practice and see that what best we can add it. And
Okay,
these
sir.
participants,
One thing I just wanted to add, sir. I
okay,
haven't slept in the night yesterday. I was preparing the slides. It's almost 203 slides and all the notebooks I've just created yesterday.
okay,
In the morning, I felt sleepy, but after seeing the participants' enthusiasm, I completely sleep is gone. I'm hyperactive right now.
very
I'm
good,
feeling very
very
happy.
good, very good. Uh, Thanks a lot, Navneet. And I
Thank you, sir.
hope that participants, those who are working in different institutions or the industries, knows about now the overall glance of the seminar, that is workshop which we are conducting it. And now today's session, which is being shared by Navneet, and his potential also you know it, you can also use him over there in the right time at the right places, so that he will also wants to share his knowledge with you all. And he is quite flexible, and he was being attached with this Ramakrishna mission, where we are working together with him, not only for MSc Data Science, even for MCA and other classes also. So participants, thanks for your participating in this, and thanks Navneet for your presentation. We hope
Thank you,
that
sir.
we will be meet you tomorrow. Tomorrow sessions will be focused on uh, dimensionality reduction, decision tree, feature engineering, and by Sandhya, and also by Dr. G. Suresh, who will be concentrating on multi-class and multi-labels over there. So both the people will be taking up the sessions, 2 sessions of Sandhya and 1 session of G. Suresh, who is also the co-founder of the Passive Labs. So both 3 sessions will be there for tomorrow. So we will meet you tomorrow morning at 9:30 over here. Thank you all for the participant, and thank you Navaneet for your active participant and making the sessions very lively and interesting. Thank you all.
Thank you, sir. Bye bye. See you guys. Bye.